One thing that I did want to show you, and I'll go ahead and pull up your Schoology course, and that is the resources for your AP review. So what I did was I created another folder. This is going to be our last folder of the year, where this is where I'm going to start putting the things that we do for the review. This APAB Calculus review was the one that I did while I was skiing at the end of January. So that is one that you should have already done. And it was, I thought, a fairly decent review of things like limits and derivatives and a lot of the background behind why we can do what we do with average rate of change and instantaneous rate of change and all that working together. So if you never checked your answers, if you never finished your answers, there they are. Oops, I didn't click that button. In this folder also, this is the most recent one that I put, and if you were absent last class, maybe you didn't get it, but we'll go ahead and pull it up. This is the 8 days of Delta Math, and my intent was for you, and in a moment you're going to get a chance to go up and pick up materials, and if you're a person that needs this, it's here. If you weren't here and didn't get it. But what I did for this one is I went through and I listed every single topic that we did. And if the numbering is off, it's because there's a BC topic in between that we get to skip. But then what I did was I assigned you Delta Math problems for you to review. And it's interesting. We have a bunch of different curriculums that are all knitting together right now. The first one is what College Board says we need to learn. That's the primary driver behind what we do. The program that Mr. Logan and I are using with the notes and the practice is the second version. Delta Math is a third. Having the different perspectives of the way that problems are asked is good, so that you have different wording and different access. The Delta Math is particularly good because the program that we have, now that we're paying for it as a school, you get video support that's helped. So maybe those videos will be helpful for you. If you get it wrong, you can click on an explanation. It'll tell you why you got it wrong. If you feel like you need more practice, then you can ask for more problems. So in a lot of these, I only gave you 1 or 2 problems to do, so I can give you a lot of variety. But if you feel like, gosh, I really need more practice on this, then you can always ask for more problems. It is time for you to make a very, very, very difficult choice, and it's opposite of what's intuitive. We like to do what we know how to do, and that feels good. When you do something familiar and easy, the University of Chicago just released a study that if you are a person who is stressed and you're overwhelmed, watching a TV show that you've already watched is your brain's way of relaxing because it's a comfortable program, you know the outcome, and it resets you mentally. Any of you watch shows on repeat? So if you're a person that watches the same show, I think my daughter's gone through Grey's Anatomy 4 or 5 times from start to finish. So those programs, they're comforting to her. She feels in control. She knows what's happening, kind of thing. University of Chicago just said that's not laziness. That's you making a choice to reset and calibrate your brain and going to the familiar and feeling good and feeling in some kind of control. I found that study fascinating. If you need to do a couple ones where you're like getting the successes and the green check marks, that's fine. But it's not just about doing what we know how to do. It's doing what we don't know how to do and learning from those mistakes. So doing Delta Math that you already know how to do is a waste of your time, unless you need a few atta-girls or atta-boys to make you feel good. Are you with me on that concept? So I'm not collecting this, I'm not grading this, I'm not giving you any kind of grade. All of this stuff is just for your use as a student of calculus. And then the rest of the page is blank for you to take notes on different things that you learned from that unit. So I gave you a screenshot of each of the things that you can do. If you need only one review of the quotient rule, don't do two. You get one right, move on. I'm not grading you on completion, but I'm having everything that we studied along with the Delta Math and opportunities for you to take notes. At the end of this section is a pretty cool area where I have additional Delta Math practice, and they have these calculus flashcards. So I don't know if any of you dipped into this yet, but it's pretty cool. So you clicking on this gives you kind of like a mixed bag of things to make sure, and bring that up to the, like stirring the pot of soup, just bringing it back up to the front. And then looking at some of these particle motions, velocity, acceleration, position, conversations that we want you to be able to be good at. On the back of the packet is some conversations about exam details. Miss Anderson's going to come in next week. I think I have her coming in to talk to, maybe it's this week, I'll have to double check my dates, to talk to you about the test and what you should bring, and making sure that you understand the format, how it's a hybrid, some on computer, some with the blue book, some written, whether you need black and blue pens, pencils, batteries, whatnot. If you are a person who does not have a graphing calculator that has the functions we've been using, Math 9 and the exponent key, store, and that kind of stuff, then you definitely want to make sure you take a purple sheet, fill it out, and I'll get you one of ours. You can't take the test with a yellow calculator. I can't give you one of our class calculators, but I can get one for you that has those functions. So if you don't have an updated version of our calculator, you want to get one, and you can't ask me on it on exam day. So make sure you have that. And we'll be talking about strategies and whatnot as we continue going through. But for a lot of people missed class last week or 2 weeks ago, so I want to make sure that you know that that resource is up there. Are we good? Okay. Some of you already took a deep dive, so it was neat. I went on to Delta Math, and I can tell who's been working and who hasn't. So that's an interesting window. All right, when we were together last, we talked about this area between curves, and I tried to get the one website working, and it wasn't. I think I have it primed and set up for us now. So let's see if I can get you looking at this. And I think what I'll do is I'll start on the other side of your warm-up first, because this website is the one, and both of these are posted on Schoology, by the way, is for you to play with and understand what we are talking about measuring volume. That integral simple is what allows us to find the antiderivative and the accumulation of change throughout. So on the back of your paper, I went ahead and I copied this picture. Sorry if it came out too dark with this gray, but if we have these two curves, and we've seen, just for simplicity's sake, our square root curve, which here's the red, and our x squared curve, which is our blue, and those two curves create that area in between. When we're looking for calculating what that area is, that is our integral when we talk about the one curve minus the other. So that adding up of all these different little lines and adding up all those different areas, the area, and adding them up, is that difference between the curves. That was step one. When we got to the second half of this unit, the conversation became about, let's have that be the base of a solid figure. So if I look at my cylinder here, basically what you're looking at there is this base. So this here, you're looking at this base has this shape. But we want you to understand it in a 3D aspect. And we can do these measures of how we add up that shape with this base and then add up this volume. And what we do is we can take slices. And the conversation is, what kind of slice do you want? Because if we do square slices, that means that we can find that volume throughout by taking the area of this square plus this one 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 plus this one, and that accumulation of area slices is going to represent our volume the same way as how this area of the base times height represents our volume, where I repeat this slices on up. So as I take the area of all these slices, and sometimes they want us to use triangles. Okay, then I find the area of the triangles and I add them all up. Sometimes they want us to use semicircles. Okay. And what's cool is this idea way back in August when we talked about the idea of a limit. What if I had 58 half circles? 59, 60, 61. Would I be more accurate if I had 100 half circles? What about 200? How about a limit as n approaches infinity? And that's how we understand that accumulation and represent that volume of that space from start to finish of the curve, from A to B, from the beginning to the end. So what each of these topics has us doing is taking that volume, and we can make those measurements with respect to the x-axis, and we can do it whatever axis we're talking about. The lines we draw, the little sections we draw, are going to be perpendicular to that axis. If we're doing it with respect to x, we're doing it with respect to y. And that determines what our boundaries are. If it's with respect to y, it's your high-lows, right minus left. If it's on the x-axis, it's start to finish, top minus bottom. That gives us that area. Do me a favor and with your partner, spend a couple minutes talking about the formulas for areas, rectangles, isosceles triangles, equilateral triangles, and draw some sketches in this space. So what I'm looking for is you to draw what you saw on that. This is the distance between the curves, and I'm going to be able to find that area, but then the volume comes from adding up all these squares. Our rectangle conversation was different because sometimes we can have our height be constant. Sometimes our height is 3 times the width. Sometimes our height, so we end up with, instead rectangles, we end up with your area equal to length times width as opposed to sides squared. 2 kinds of triangles we talked about, isosceles and equilateral and semicircles. Draw the shapes. If you want colored pencils, you can pick some up here. You're going to want some colored pencils for today's lesson. So get up, walk around. There's a box here, a box there. I'll give you a couple minutes to draw and talk. Go. All right, so just take the time to draw those shapes, and I really want to draw your attention to the difference between a square and a rectangle. Where the squares are widest, they're going to be the tallest. So think about that because you're going to have my length and my width be the same height. For my rectangles, depending on whether I have a constant height, 6, or whether the constant is twice or the height is twice the width, then still at the wider parts, it's definitely going to be taller. So that changes that shape that we're finding the volume of. The equilateral triangles are going to be the ones that we can see in the program. It's the isosceles triangles that the program doesn't show. So that triangle is going to be as tall as it is wide, but half of that area. So you want to make sure that you pay attention to that part there where it's half of that square. If you are a person who struggles to remember this formula, a lot of times what I'll end up doing is quickly sketching an equilateral triangle. I'm trying to find some space here. If I draw an equilateral triangle and remind myself that that's half of a 30, 60, 90 triangle, and if I go back to my 2x and x from geometry, then I don't end up at that formula. Now that I'm in calculus, I can remember if this is x, this is half of x, and that this length here is 1/2 of x times the square root of 3. So my area is going to be equal to my base, which is x, times my height, which is 1/2 of x square root of 3. And then don't forget all of that is divided by 2. So that's where you see your root 3 over 4 times x squared. So if you can't remember the root 3 over 4, here's your root 3, here's your over 4, there's your side squared. So if that formula isn't one that sticks in your brain, you can go back to your geometry and rebuild it from your special right triangles. All right, so that was what we were doing already, but I want you to have those pictures. We've already explored that website. The next website, go back on the front of the page, and what I want you to look at now is what we're talking about in these next lessons. And the next 4 lessons are all very, 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 very similar. So it's worth really deep diving into the one that we did last Thursday. If I'm taking the area between the curves, I'm going to go ahead and take my f of b minus my f of a. If my f of a happens to be the axis, that's awesome when I'm working with that. When I'm looking at a volume conversation, we talk about this idea of spinning around the axis. So this curve then is rotated and spun, and then I can see the 3D shape that it's making. All right, here's our arts and crafts project. I gave you all a post-it note. So would you please, there's post-it notes on your desk. And what, anybody not have a post-it note? Grab one. Everybody got a packet of post-its, just take one. And what I want you to do is, you know how post-it notes have a sticky side? I want you to fold sticky side to sticky side. So sticky side to sticky side looks like this, right? Right? Anybody feel this way? Sticky side to sticky side. Okay. So what I'm going to do now in my post-it note where I have it folded, and here's my sticky side stuck to sticky side. Everybody okay with that? What I want you to do now is draw a curve. So go ahead and with your pencil, draw a nice whatever curve. And then go ahead and talk about if we wanted to find this area in this curve. Rock, paper, scissors with your partner to see who comes and gets a pair of scissors, because what I want you to do is I want you to cut along this curve. You all picked up a skewer when you walked in. What I want you to then do is take that skewer and put it through the fold, and you'll find yourself with a curve that you can rotate around the axis. I gave you a couple things of Post-its So if you need to practice and do it a couple times, you can. But here's how it goes. Hang on with me just a minute. Here's my curve. Here's my cut. Curve cut. Here's my skewer. What we're doing in these next 4 lessons is spinning this bad boy around the axis. We are spinning it around the axis. So if you have extra Post-its, if you screw up, but what we're doing is we're finding this A and this B where your curve starts and stops. And we are spinning this around the axis. And if we spin it around the axis, you get this kind of a shape that's solid. So if you spin it around the axis, now here's the thing, I keep holding it like this where it's the x-axis, but guess what else I can do? I can spin it around my y-axis. So that curve that we draw, if you cut too much of your sticky stuff off, get another one. Because this curve, I like the shape of Luke's curve. Hold it up in here. He's got a nice little like hourglass, like looks like a vase, or you know what I mean? Like he did something a little bit more exciting than. But you can see that when this is revolved or spun around the axis, if you're having a hard time picturing what's happening, what we're doing, we're finding the volume of the shape that would happen. If you've ever watched a 3D printer go, it's kind of cool. It's amazing how it creates this 3D shape from a picture, and that's what we're doing. It looks like this is like a cone, like a party hat that you can put your hand inside. It's not, because each of these are discs. Each of these, it's a solid shape that are discs, and we're finding the volume of the shape. And depending upon which axis we spin it around is what math we use. And we're using circles, but the program that I put the link on Schoology, if you want to use it, the program says if you want, you can go ahead and use diamonds or semicircles or triangles that are isosceles. We can do squares. We can do rectangles. So we're doing, just for our purposes, circular sections, but that volume of what we're getting spins around. And that's what these pictures are on your warm-up when you're looking at this curve that you spin around. Now, if you're looking at each of these equations, this is with reference to my x-axis because y is solved for. This is in reference to my y-axis because x is solved for. So you got to get real tight with understanding, am I spinning around my x or my y-axis? And what does that look like? Keeping in mind that your discs are always going to be perpendicular to whatever axis you're talking about. This game is one that we can play. That's the Towers of Hanoi, I want to say. And last Thursday we were playing it a little bit when we had to. The goal is to try to get this whole pyramid to one of these other sticks. You can only move one at a time. And the process is to go ahead and you can never put a bigger on a smaller. So if I do this, I have to get this guy over here, then this guy, then that. So eventually you want to get the whole thing. that's not our purpose today. Our purpose is to see the discs. So we're measuring the area of each of these discs and adding them up. The confusing part about this is the radius of these discs is 1/2 of this distance between the curves. So you have to think carefully about what it is we're spinning in the discs. This disc here, this triangle shape gives us this party hat. And when we start talking about the radius, we need to make sure we remember each of those discs when we're doing pi r squared, that r is 1/2 of that distance between the curves. All right, here's our next and final lessons for this class. Am I going the wrong way? Once we do our little post-it project and you draw a skewer and rotate it, we have 4 lessons, really 3, because we did 8, 9, where we did the disc method around the x or y axis. Today we're taking that disc method and we're just doing a translation. We're either going up or down the y-axis or left or right on the x-axis. And here's those pictures here. Here we have the discs with respect to x, and here we have the discs. Luke, this looks like your curve. We have the discs with respect to y. So if you've had a hard time picturing this, visualizing, maybe the post-it note and the skewer helped. I don't know. Yes or no? No? What happens next is kind of cool, because if I take a look at my curve here and I draw a second curve and we go back to, again, looking at this x squared and square root curve, if I have those two curves together, now when I spin it around the axis, I end up with a hole in the middle, and that hole is going to be this washer where we have to subtract the circle, the volume of the little from the volume of the big, because there's a hole. So you have the Post-its and you have your skewer and you have your scissors, but playing with it and seeing it, you go super fast and make it all blur into one, like a, do you guys do that with sparklers? You know how you write your name with a sparkler? But maybe seeing that will help you with this next couple lessons. Sound okay? All right, I'm gonna give you 30 seconds to touch base with your partner, another 30 seconds to return your materials. You can keep the skewers, happy birthday. And if you want to make more Post-its, rock on, but we're gonna start the lessons in a minute, go. All right, so when we were together last, we went ahead and did 8, 9, or at least we tried to. And what we want to talk about is when we talk about the area bounded by the equation, we have to pay careful attention to what it is we're talking about. Y is equal to 0 is that x-axis, x is equal to 2 is this line. And then we're going to revolve it around to make it look like a solid, or to create a solid, understanding that each of those cross sections, if you want to, I like the word disc, that they are those little discs. So if you think about each of these little discs, you know, how many tiny slivers can I make of that shape? It helps me to draw a little arrow to show how my curve is rotating around this x-axis. The radius of the circle is going to be, and make sure you understand that this is the difference between the curves. So if here is f of x, and I know I'm looking at y is equal to, then a lot of times we don't do this minus 0, but today we're going to move this up and down the axis so this conversation becomes important. we can go ahead and call that f of x, that output, we can call that our radius. And understanding at all the different parts of the circle, that radius is different at all the different parts of the graph as it grows. So our area is pi times radius squared, that same area formula that we've been memorizing for years. Our volume is going to be from whatever boundary to whatever boundary on this x-axis you're talking about, of all of those areas added up together. So that integral, go back to when we first learned that symbol, think of it like the sum, the summation, the accumulation. It is going to be the accumulation of all of these little area disks on this interval from here to here, adding up all those little areas together. So here you can see, if I'm talking about the area of all of these little disks, it's, if I wanted to find volume in a 3D sense, it's all these little areas added up together. That's what gives me my capacity, my third dimension, my length and width and height. Okay. So now our volume of a solid of revolution, our volume is equal to, from A to B of pi r squared in terms of x, making sure that you're keeping track of whether you're talking about things revolving around the x-axis or the y-axis. R is the distance between the axis of revolution and the outside of the solid. So the tricky part about these is if we're doing them quickly and we have a calculator and we can do math 9, then we get spoiled and forget how to do the antiderivative. Because there's a lot of these kinds of things on the non-calculator section of the test. So if you're taking the calculator section, and the practice problems for this unit, they go ahead and they just say, just write up the integral, because then it's just a practice of do you get clumsy thumbsies, can you type it into the calculator and get that right value? We do have to spend some time practicing them without the calculator, reminding ourselves of things that we've already done, like finding this integral and using u substitution, and remembering that once we translate it into terms of u, that changes our boundaries, plugging in those values into our u equations, and making sure that we adjust. A lot of times your exam will give you questions about, please give us to this in terms of pi. If they ask it for you in terms of pi, then pi should be in your answer, and your answer should be a rational value, because that your rational value pi hasn't factored into your answer yet. Do we run out of time? And this is where we stopped. And it says yes. Because when we figure out, I don't know why we didn't finish this, but we'll go ahead and finish this now. When we're finding this, volume is going to be equal to pi over 2 times e to the 6th minus e to the 0. Anytime you do anything to the 0 power, it's equal to 1. Oh my God, be so careful. Don't think it cancels out, because it's e to the 6th minus 1. So your volume, if they ask it to you in terms of pi over 2 times e to the 6th minus 1 is going to be the answer that they're looking for. Making sure that we do units. What do we have here? Revolve, find the volume of the solid formed. If they don't tell you what the units are, make sure that you tell them that you know you're dealing in cubic units. Getting my geometries, a ton of them, they just got their polygon test back today and they're so mad at me because I took off ridiculous points for units, which I can, so I did. So if they don't include any units, then they lose points. But if they include the wrong units, if you're talking about volume and you don't do cubic units, that's not volume. If you're talking about area and you don't talk about how many little squares fit on a two-dimensional surface, that's not area. So we need to make sure that we have the correct units in our conversation. Everybody okay with that? All right, this other one, take the region bound by y is equal to 4 minus 2x, y is equal to 0, and x is equal to 0. Revolve this region around the y-axis. Once I'm revolving around the y-axis, you take your little toy and make it the y-axis, because now you're spinning it this way instead of this way. So we want to make sure if we're talking about the y-axis, we're talking about disks this way, and our radius is just going to be equal to 1/2 of that disk width. The number one thing that we have to do here is always solve for our x value. So if y is equal to 4 minus 2x, we can go ahead and, depending on how you want to, so 2x is equal to 4 minus y divided by 2. We can say x is equal to 2 minus y over 2. And we want to make sure that that's our equation that we're using when we're integrating. You're looking for the sum of all the areas from 0 up to this point here, and you find that with your intercept. Your absolute y, so our 4 goes there. And you want it to be of all of these little disks, their area is pi times 2 minus y over 2 squared in terms of y. When you're putting this into the calculator, that's pretty easy, no problem. If you're having to integrate this on your own, pi comes out of the integral from 0 to 4, and this is going to require some FOIL because you don't know how to integrate that as it's written. You're going to go ahead and do first outer inner last. So we've got 4 minus, what's that going to be? 2 times pi over 2, right? 2 minus y over 2, 2 minus y over 2. My outside or my inside terms is just negative y. My outside term, negative y, so it's going to be minus 2y. And then plus y squared over 4 in terms of y. Am I okay? Do you agree? So when I do my antiderivative, I feel like it's been ages since we've done this. It's going to be pi times, this becomes 4y minus y squared plus, this becomes y cubed divided by 3, 1/12. And that's from 0 to 4. Oh, what'd I do?
I was just curious about something.
Go.
I missed something. How do you get 4 as your denominator?
How do I get 4? Oh, because when I'm looking here, if it's in terms of x, I'm looking for my boundaries on the x-axis. Here I'm looking for boundaries on the y-axis, and I know that this graph intersects my y-axis at the y-intercept. So whether this equation is in terms of x or y, that point over 0 up 4 is going to be a solution to the equation, so I can use my slope-intercept form to help me get that value. Does that make sense? How are we doing? So then this is definitely going to be some calculations for you where you have to plug in 4, for each of these. And then minus plugging in 0, but that's easy because they all have y's in them, so they become 0. So we'll say it's pi times 4 times 4 minus 4 squared plus 1/12 4 cubed minus, and then we end up with 0, 0, 0. So our answer here is pi times 16 minus 16 plus 4 cubed 64. Half of that is 32. So our answer looks like 32 pi. And that's a, what did I do?
That's over 12 now, too. That's the,
Oh,
yeah.
big difference. You can put a Smarty up. Thank you. 16 minus 16. So this is 64 twelfths. What does that simplify to? 32 sixths. One more, 16 thirds. 16 thirds pi. And that's units cubed. Thank you. Yeah, total fair game question without a calculator. So if they do that to you, they'll end up asking for you, obviously the answer in terms of pi. So that's something you need to be able to do. Your volume is equal to. If you've had a chance to move on and do these, my advice to you is you don't have to do them. You don't have to do all the practice problems, but just if you're good at understanding the concept of it and your area formulas, writing is no big deal. Looking at the x or the y-axis, etc. Are we okay on that? Okay. So now we say, taking this disk method and we're revolving the things around other axes. So if you and your partner want to put your skewers together, the conversation becomes about if this is my x-axis and I move my shape up and I'm revolving it around a different axis. If this is my y-axis and I'm moving my shape over and I'm revolving it around a different axis. So we're not having you revolve it. Max asked a question a couple weeks ago where they were like, okay, well, what if it's a linear equation, like y is equal to x, or like, y is equal to 2x minus 3. Like, well, we're not doing that. We're just only moving it up, down, or left, right. And instead of having that y or x axis, then we're just going to have another horizontal or vertical line be that boundary marker for us. So, okay. Recall the volume of a solid, which we already know is the accumulation of our pi times our radius squared in terms of x, if it's over in reference to our x variable. But what I want you to do is take a minute and talk about what this represents. I want you to talk about where does this value come from with your partner. Write it out. Go.
So that would be the
So understanding, and a lot of times when I'm doing these, I'll find myself talking to myself where I'm talking about, okay, my volume is equal to the accumulation. Every time I draw that integral sign inside your head, you should be saying accumulation, you should be saying sum, like whatever reminds you that that's all those things added up together. That's that antiderivative. When we were taking a derivative, we were breaking things down into rates of change. Our integral is building them back up. So when I'm talking about the accumulation of all those itty-bitty disks, that A to B is the region we are bounding. Where are we stopping and starting? And that should help you with our X or Y conversations on what you're doing in your axis. Pi r squared, that radius is the radius of the disk, but that's also the output of that function. So if I have a curve the point on the curve that I'm using. And the thing is, what's crazy is none of these discs don't have the same radius. So it depends on where you are. This point here is the output of that function that determines how wide that disc is. So understanding that not all discs have the same radii, that's an output of this function, is important. All right. If we're finding the volume of the solid formed revolving the bounded region about a line, they asked us to set up the integral, but don't evaluate. What I'd like you to do is go ahead and draw a little sketch of what you think these equations look like for each of these. So with your partner, I just want a sketch of what you think our areas are. Go ahead. All right, so take a look at my drawings and see if you agree. Y is equal to 3 minus x squared. I know I can go up 3, that's my intercept, and the opposite of x squared is going to give me this down like a frown parabola. My green line here is at y is equal to 2. My horizontal line with the slope of 0 with the y-intercept and a y in the equation. What's crazy is that they're asking us to now revolve this shape around this line. And the only thing that I want to revolve is the area between the curves. So if you look at this curve here, what I'm going to do is spin it around this axis. So what I end up with is kind of like a little football shape. And it's just spinning around that area between the curve around those two axes. Here, when I'm revolving my 2 minus y squared, the same logic where I go up 3 and then negative x squared is this parabola. Here's this logic where I go out 2 and my negative y squared is going to have this shape. Here's my x is equal to 1. So in the same vein, I'm going to take this space in between them and I'm going to spin it and get that kind of shape. So the colored pencils might be very helpful to you to be able to see the difference between your axis and your horizontal or vertical line where your rotation is happening. All right, so they asked us to set it up, but they don't want us to solve it, so that's good news. Hey, our step 1 is going to be to find A and B, because what we're looking for here is the integral of some boundary to some boundary else. So this has to be what we're looking for in terms of A and B. So here we go back to algebra 2, where I'm going to set my two equations equal to each other and say, okay, if they are both equal to y, they're intersection points, I can set them equal to each other. And I can say that x squared is equal to 1. I added x squared to each side, I subtracted 2 from each side, I took the square root, and x is equal to plus or minus 1. So when I go to set up my integral, I know I'm going from negative 1 to 1. That volume is going to be equal to the sum of all of these little discs from A to B. All right, so that's my first conversation, find A to B. My second conversation is going to be to find your radius. And your radius is going to be the difference between these two curves. So when I look at my radius, that's going to be my upper curve, 3 minus x squared minus 2. I can of course simplify that to 1 minus x squared. So when I'm finding my volume, I want the sum of all these little disks from A to B. Those disks have an area of pi r squared. So those disks have an area of pi times my radius squared in terms of x. A second way of thinking about this is, and I'll move this up a little bit. A second way of thinking about this is, what if I took this entire story and subtracted 2 first? And I can do this because I'm cheating and you can't. But what if I went ahead and instead of finding the areas between those curves, what if I just subtracted 2 so that this entire conversation was still happening around the x-axis? Because my intersections would still be the same, and I would be looking at the same kind of conversation about this radius minus 2. And we'll talk about that shift, whether you do it while you're thinking and working or after you've already done it. But the work turns out to be exactly the same. All right, let's talk about this guy. If I have x is equal to 2 minus y squared, x is equal to 1, revolve around the line, x is equal to 1. With your partner, will you go ahead and find a and b and see if you can set up that integral? On your mark and set, go. Do we agree? Did you get your dy instead of your dx? It was a nice easy intersection, no problem. All right, let's talk about one that's not as pretty. So when we talk about y is equal to the x minus 3 and y is equal to negative 2 and x is equal to 3, they want us to revolve around the line y is equal to negative 2, that horizontal line. So let's go ahead and draw a sketch of what you think those graphs look like. 2 to the x, I know, is a exponential graph that looks like that. Every exponential graph has that point at the intersection of over 0, up 1. Are you okay with that? What does negative 3 do to that graph? It shifts it down 3. So if I think 1, 2, 3, depending on taking this point of 1, 2, 3, my asymptote is going to become, instead of my y-axis or my x-axis, it's going to become that line y is equal to negative 3. You okay with that? And it's important to show the asymptote because that's not necessarily the graph that I'm, the line that I'm revolving around. Because I'm revolving around the line y is equal to negative 2. So we're going to do that in a different color because this is my line of my axis of revolution. And my reflection of my graph is gonna go this way. And what I'm measuring is these discs here. From where to where? From where they intersect here at 0 to x is equal to 3. So if we have that line here of x is equal to 3. So if we're revolving it around this, we need to understand a couple points. I need to know this point, this xy ordered pair, and I'll do that by solving the system of equations. And that is, when does y is equal to 2x minus 3, when does that equal to, x is equal to 3, we can go ahead and plug this value in for x. My output is equal to 2 times 3 minus 3. My y is equal to 5. Over 3 up 5. And this point here, -2, is going to come from, if I'm going from this axis of -2 no, this here is this point up here. This is my radius. That's what I wanted. Yeah, that's where it hits the line. Because that's my radius. There we go. I like that better. So each of our radii is what I'm spinning. So when we talk about what that radius value is, that radius is going to be the difference between your curve, 2x minus 3, or 2 to the x minus 3, subtracting my other curve, -2. So my radius value, 2 to the x minus 3 plus 2, 2 to the x minus 1. When I write my volume is equal to the integral from my a to b, that's going to be from 0 up to where my integral was stopping, to 3 is my boundary. And I have my pi r squared and my radius 2x minus 1 squared in terms of x. Yeah.
Where did you get the green down, just like the light green downward curve from?
That is what happens when I take my curve and I spin it. That's its reflection.
Oh, okay.
So that's if I have my curve like this, but then I look at it and spin it. But I don't need this intersection because all I need is the radius for each disk that I'm calculating the area. So pi r squared is going to be the area of each disk at the different x's. So the fact that this here is your variable, this x here, is what determines how wide the disk is at each of your different values. That's this output here on that graph.
So your expression for the radius, can you just explain kind of the volume in the red?
It's the same as the area between the curves. So 2 to the x minus 3 is my exponential curve that goes this way, and y is equal to -2 is my axis that I'm spinning it around. So I'm finding the area between those two curves by finding the difference. There will be times, and one of the hardest things that I have to do for my geometry kids is when we talk about the distance formula and I give them this template, if we have 2 points, not try to keep it easy, 0, 5, and 5 to 10. If I have 2 points on the coordinate plane and I want to figure out those distances between them, it freaks the geometry kids out if we do our difference in the x's in a different order. So if I say the difference between these x's is 5, inevitably somebody said, well, I did 0 minus 5 and I got -5. And I went, that's okay. Because we're going to square that distance, and whether I did 0 minus 5 or 5 minus 0, we still get a distance of 5. But if they have a negative here, no matter what, we're both getting 25 when we square that negative away. Are you with me on that? If we talk about this distance here from 5 to 10 or 10 to 5, same story. Doesn't matter how we do it, we're squaring that value and that negative squares away. Now, the geometry kids still screw up all the time, because if I ask them to square -5, they do this noise and try to convince me that -5 squared is -25. Like, no, it's not, because a negative times a negative is a positive. Your calculator knows order of operations. Your calculator looks at this and thinks it's -1 times 5 squared. This is what your calculator reads. Because order of operations has you doing exponents first, and then order of operations from left to right. If you want to square -5, it has to be this story, because -5 times -5. And I end up talking with this about the geometry so much, because sometimes when I'll put a negative in, when I'm doing the work in front of them with the calculator, I'll just drop the negative. It's one more key I gotta press, I'm not gonna bother. And they're like, Smarty, you didn't do the negative, you did the negative. I'm like, I don't wanna do the negative. Because when I square it, it's still gonna end up being the same thing. If you're wondering what my point is, if you're taking a multiple choice exam and the answer is 1, pi times 1 minus 2 to the x squared, that's a correct answer. Because if you choose to look at the shift of what's happening, top, bottom, top, it doesn't matter, because whether it's a positive or a negative value, it's going into the calculator and becoming squared. So if your calculator has what's in red, or if your exam has what's in red over what's in purple, it's okay, because there's 2 ways of looking at these shifts. If I wanted to do that radius by moving my graph and counterbalancing that, I would get the same radius. Alright, so that's it for this lesson. What you have on the back is practices, and again, I kind of love it when they say this, because then I feel like it's more efficient getting to what they think we already know. We know how to do the antiderivative and to calculate those integrals unless we've forgotten how. So if you feel like you need some practice, that might be one of the things, because that's still fair game that you're asked to do that. All right, I have your quizzes graded. You have about 10 minutes to either go online and do some Delta math, work on these, kind of process this a little bit for these last 2 units or these last 2 lessons at the same time, okay? All right, so come get,
Says you're still recording.
okay, was I not recording before?